lecture we had seen how one can make use of the inductance expressions that we have derived in order to write down the voltage equations for a 3-phase induction machine and then a 3-phase synchronous machine. We have seen that these expressions are fairly long and the system size, system description is fairly big. In the case of induction machines, we have 6 variables on the electrical side and then 1 variable on the mechanical side, which makes it a 7 variable description. In the case of a synchronous machine, we had considered 2 windings on the rotor and 3 windings on the stator, which makes it a 5 electrical variable description, and then you have the speed, so the 6th variable. So it is a 6 variable description, and the description is also not very simple. It involves a lot of rotor angles and then mutual inductances, all those things are there. So the question is, how do we simplify these machine description in order to make it more understandable and in order also to make it easily analyzable, so that you can do an easy simulation on any digital computer that you might have. So for this purpose, let us look at these machines one by one. Let us take the induction machine first. In the case of the induction machine, as I said, we have a 6 variable, that is electrical, and then 1 mechanical variable as well. And this induction machine is a 3-phase induction machine, which means it has 3 phases on stator and 3 phases on the rotor. That is what we have. And in order that the induction machine works, we have seen, you would have definitely seen in our first course on electrical machines, that the induction machine or any 3-phase AC machine, a 3-phase winding, produces what is called as a rotating magnetic field. And since we have now understood how the magnetic field and the magnetic circuit is to be analyzed, we know that a magnetic field is, or the magnetic flux is generated by an MMF that exists, and therefore if there is a rotating magnetic field, we can also talk in terms of a rotating MMF waveform. This rotating MMF waveform is the net of excitation on all the 3 phases. For example, in order to derive the expression for inductances, we have looked at the MMF distribution around the circumference of the induction machine, of the electrical machine, in the air gap, and we had looked at one phase, how the MMF generated by one phase is distributed around the air gap. And this MMF waveform, what we had drawn was a trapezoidal waveform for a distributed winding, and this is for a specific flow of current IA, some value. For example, let us say IA equal to 10 ampere. This is the distribution having a certain amplitude and then a certain region where it decreases. All this depends upon how many turns are wound in the phase that we are considering. We also said that in our analysis it is sufficient to consider only the sinusoidal fundamental component of this. So you take the fundamental component. This is a fundamental component of one particular phase. If this current is at this level, let us say this is the MMF that is produced. if the current now increases, then a higher MMF would be produced, higher amplitude MMF, and if this current decreases, a lower amplitude MMF would be produced. If this current reverses, then this MMF would then reverse, and therefore what you have is that if this current is going to change in a sinusoidal manner, you would have an oscillating MMF waveform around the circumference of the air gap. This x axis refers to the angle around the circumference, and this may be the MMF. Now, if you consider the MMF of another phase, that would also have a similar nature, that means it would oscillate if you give a sinusoidal waveform to it, but the difference being that MMF is displaced with respect to this MMF by 120 degrees, and it would then oscillate here. And if you take a third MMF that is further displaced by 120 degrees, and therefore you would have something like this, and so that again oscillates in its own plane. The net result of all these things, if you could do that, is a sinusoidal waveform that then moves with respect to time. So, if you add up all these things at every given angle for sinusoidal excitations that are 3 phase, that means 120 degrees displaced with respect to time, then you would get a sinusoidally varying MMF waveform that moves with respect to time and has a constant amplitude. So, you get a moving waveform which in a circumferential air gap is nothing but a rotating MMF. There are good animations of this in the NPTEL web based course on electrical machines. One can take a look at this to understand how this rotating MMF is generated. Now, this is a rotating MMF, that means what you have is, if you mark an angle which represents 0 degrees as you travel around the circumference, then the instantaneous amplitude, that is, this is a sinusoidal distribution around the circumference of the machine, and this sinusoidal distribution of the net MMF will have its maximum amplitude occurring at some particular angle, and as instants at different instants, this is going to occur at different angles, and hence you say that it is rotating, which therefore means that one can describe this net MMF as, for example, one can call it as F is equal to F hat into maybe sine of alpha, where alpha is this angle. And we also know that as t increases, this is going to be at different locations, and because of that we call it as a rotating MMF. If you now mark this angle at which this instantaneous peak occurs, let us say is this angle may be 90 degrees. So, one can represent this amplitude by an arrow. At another instant this occurs at a different angle, so this arrow has moved. At yet another instant it occurs at some other place, so this arrow has moved. And with respect to space, then at any given angle, if you want to find out what the amplitude is, you can take the horizontal component of that, and then that will then determine the instantaneous amplitude at any given angle. Now, this interpretation looks very similar to that of your normal phasor representation, which you use for an electrical, let us say IA, you would call it as some Im cos omega t, and then you would represent this as a phasor with respect to a horizontal axis which is rotating with respect to time. Here also there is a very similar situation. You have a sinusoidally distributed entity here which is the MMF, and that MMF we find is rotating in space, and therefore if you represent it by an arrow, that arrow is really rotating in space, and therefore we can describe this also by a phasor, and this time this phasor is called as a space phasor, as opposed to these variables which are then called as time phasors. Note that these phasors are rotating with respect to time, these phasors are also rotating with respect to time. Here the variation of the phasor is sinusoidal with respect to time, here the variation of the phasor is sinusoidal with respect to space, and that is why this is then called as a space phasor. Therefore, given this arrangement, we can represent the net MMF generated by the three phases of the stator by an arrow which is inclined at some particular angle at a given instant of time. At some other instant of time, the maximum amplitude would occur somewhere else, and therefore the phasor should be rotated, right. So, this is the effect that the three phases of the induction machine is going to give, and it is because of this rotating phasor that the machine is able to start and run at some speed. So, if this is going to be the net effect of excitation in the three phases, we could arrive at this phasor amplitude and the angle of the phasor at any given instant by writing down a mathematical expression of the MMF generated in each phase. Remember that the axis of the A phase we took to be horizontal, so this is the AS axis, and the axis of the B phase is 120 degree away from that of the A phase, and axis of the C phase is 120 degree here. So, this is BS and this is CS. You might also remember a few lectures back we had also demonstrated that the net MMF generated by these three could be rotating in space by considering excitation along this axis, that axis, and the other axis, and we saw that the net MMF is constant in amplitude but then rotating. So, this is the net result, a phasor that is rotating in space. We can get this by knowing what is the excitation along this axis, that axis, and this axis. So, you have three axes, the result of which gives you one phasor. Now, if this phasor is what we are going to get, we could as well describe this phasor by considering a two axis system. What we can do is take one axis along the same horizontal, we will call this as the alpha axis. We can take another axis which is 90 degrees to this and call this as beta axis. Then this phasor can also be described by the alpha axis projection of this vector and the beta axis projection of this vector. So, you have an alpha component and a beta component, which if you call this phasor as f, I can call this as f alpha and call this as f beta. So, if I know f alpha and f beta, I know f, right. So, how to find out f alpha and f beta? So, instead of having to know a component, b component and c component, we are now reducing it to two components alone, an alpha component and a beta component. So, these two components appear to be sufficient to describe the resultant MMF phasor f. So, how to get this alpha component, alpha beta of the MMF waveform? So, we are essentially saying that whether it is the alpha component, beta component that you are considering, or a, b, c component that you are considering, the net MMF should always be the same, which means that the number of turns in the phasor in the stator phase, if you have some current IA flowing in the A phase and some current IB flowing in the B phase and some current IC flowing in the C phase, at any given angle phi, if you want to determine what the MMF is, you would say IA into cos phi is the MMF component which is provided by A phase A axis excitation at the angle phi. Similarly, the MMF component acting along the B axis excitation, its component at this angle, and similarly C component along that angle multiplied by the number of turns is then the MMF component. So, Ns multiplied by Ia into cos phi plus Ib into cos of 2 pi by 3 minus phi plus Ic into cos of 2 pi by 3 plus phi is the MMF that is acting along this phase. So, let us expand this expression. So, this is equal to Ns into Ia cos phi plus Ib into cos 2 pi by 3 cos phi plus Ib into sin 2 pi by 3 sin phi plus Ic into cos 2 pi by 3 cos phi minus Ic into sin 2 pi by 3 sin phi. So, this is the MMF that is produced at this angle phi. Let us simplify this expression. So, this can be written as Ns into Ia cos phi, cos 2 pi by 3 is minus half, and therefore, this is minus Ib by 2 cos phi, and then let us take this expression again cos 2 pi by 3. So, minus Ic by 2 cos phi. Now, let us consider this one, sin 2 pi by 3 is sin 120 degrees, that is root 3 by 2. So, plus Ib into root 3 by 2 sin phi, sin 2 pi by 3 is again, so this is minus Ib into root 3 by 2 sin phi, and therefore, we can now group these terms together, Ia minus Ib by 2 minus Ic by 2, this whole thing multiplied by cos phi plus 0 into Ia plus root 3 by 2 into Ib minus root 3 by 2 into Ic multiplied by sin phi is your resulting MMF. In this expression, note that we have some current here multiplied by cos phi and some other current here multiplied by sin phi. This therefore means that suppose I had an excitation that is acting along alpha axis and I have another excitation that is acting along the beta axis, this current being IA minus IB by 2 minus IC by 2, that is here, and this current being root 3 by 2 IB minus root 3 by 2 IC, then for that excitation being provided in a coil here and a coil here, the MMF is the same, and therefore we can say that this is equal to some NS into I alpha cos phi plus some I beta sin phi, where I alpha is the current flowing here and I beta is the current flowing there. So, one can now regard the net MMF that is being produced as having been produced by two excitations alone, something here and something here. Now, the flow of current here is a combination of the currents flowing in A, B and C axis. Similarly, the current flowing here is a similar combination of the three currents. Now, we have looked at this total current being the total MMF being generated by the number of turns consisting in the A phase winding, B phase winding and C phase winding. Now, we can be a little more general and then say that you have I alpha as this current and I beta as this current. We can now define a relationship saying I alpha I beta is equal to IA, or rather we can write it as 1 minus half 0 root 3 by 2 and minus root 3 by 2 multiplied by the vector IA, IB, IC. This is what we have. So, you can see that I alpha is nothing but IA minus IB by 2 minus IC by 2, that is what you have here, and I beta is 0 times IA root 3 by 2 IB minus root 3 by 2 IC, and now you have this NS. So, multiply this by NS, and we can in general have some other number of turns here which I will call as N alpha beta. So, whether you want to choose NS as equal to alpha beta or NS by N alpha beta as some other ratio could be decided on certain other issues, which we will see as we go along. So, the equation that is going to relate I alpha, IA, IB and IC has now been derived in this manner in order to ensure MMF invariance, which is to say whether IA, IB, IC is going to flow or I alpha, I beta is going to flow in these two windings, it does not make a difference as far as the net MMF is concerned. That is the meaning of MMF invariance. So, now we see that instead of considering these three variables, you might as well consider these two variables. However, these two variables are not the real life variables, they are fictitious variables. We are only trying to imagine that a current I alpha and I beta is flowing, whereas actually the currents that are flowing are IA, IB and IC in the real three phase machine. However, since this has only I alpha and I beta, number of variables is only 2, whereas here number of variables are 3, maybe we can try to recast the equation in terms of I alpha and I beta, solution might be simpler, and then having found out I alpha and I beta by solving the machine equations, we might then try to get back IA, IB and IC. But you can at once see that it is, you can go from IA, IB, IC to I alpha, I beta by these equations, whereas you cannot go from I alpha, I beta to IA, IB, IC easily, because this is not a square matrix. If you have a square matrix, then you can easily invert it, and then you can get IA, IB, IC from I alpha, I beta, but this is not square. So how does one solve the system, solve this issue? Now you would know, definitely you would have heard of something called symmetrical components. The idea of symmetrical components is that any unbalanced 3-phase system of either voltages or flow of currents can then be resolved into a positive sequence component plus a negative sequence component and then a zero sequence component. Now you may remember what these 3 sequences are. What one can show is, if you look back on the subjects that you have learnt in order to find out what these things are, you know that given VA, VB and VC, you can determine V plus, which is this, and V minus, which is the negative sequence component, and V0, which is the zero sequence component. Or having been given V plus, V minus and V naught, you can also get VA, VB and VC. These two are interchangeable. If you know one, you can find the other. What can be shown is, if you look at the equations deriving these expressions, and if you look at the equations we have written here, one can show that if you know V alpha and V beta, it is equivalent to knowing V plus and V minus, and therefore if you want to determine a set which you can either do the transformation from here to here, or you want to go back, in order to make this description square, the information that is missing is that of V0. So if you somehow include a zero sequence representation in these equations, then we would hope to have a system where you can go from ABC to alpha beta or alpha beta to ABC. And this representation, if you remember how those are then derived, in the symmetrical component expressions, V0 is then written as 1/3 of the phasor of VA plus VB plus VC, average so to say of VA plus VB plus VC. What we want is only a representation of the symmetrical component, and therefore it need not necessarily be 1/3, it could be any number k which is then used to multiply VA, VB and VC. And therefore if you want to have a system that is a square matrix, one can therefore do it in this way. So you have I alpha, I beta, we said that the missing information was that of I0, so you add an I0 component now, the number of turns is still there to be found out, that is then equal to the number of turns on the stator. Here you have 1 minus half minus half, 0 root 3 by 2 and minus root 3 by 2. If you want the exact I0, then you should have put 1 by 3, 1 by 3, 1 by 3, but that is not really necessary. What we want is a representation of that, so I could as well put k, 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 and then this would be IA, IB and IC. So, with this description added, with the description of a representation of I naught added, you now have a square, this becomes square, and therefore one can invert this. So, if you want, if you have I alpha, I beta, I naught, you can multiply by the inverse and then get IA, IB, IC. But then we now have to determine what should be the value of k. As I said, we could fix k to be any value which gives us some ease of operation. So, what ease of operation will you look at? Now, let us say you do want to find out IA, IB, IC from I alpha, I beta, I naught, then you would need to multiply this by the inverse of the matrix here. If you find the inverse of this, what you would find is, for example, let us say this matrix is M and you want to find the inverse of this matrix, then what you would see is that M inverse is given by 2 by 3 times 1 minus half and then 0 root 3 by 2 minus root 3 by 2. And then what happens is you get 1 by 2k, 1 by 2k, 1 by 2k. This is the inverse of the matrix that we have written down here. You can try to evaluate the inverse and verify for yourself. Now, one can see that this inverse, except for these three numbers here, this matrix and this matrix appear to be related as transpose of each other, appear to be so, except for this row and that. If you really want it to be so, then what we have to do is, if you can set k equal to 1 over 2k, then this matrix and this matrix will really be M and M transpose, not exactly except for this number 2 by 3, and therefore if k has to be equal to 1 over 2k, what we are saying is k square is half and k equals therefore 1 by root 2. So, if you put k equal to 1 by root 2, then what you have is these three numbers become 1 by root 2, 1 by root 2 and 1 by root 2, and here also this becomes 1 by root 2. And therefore, what we can say is M inverse is equal to 2 by 3 times M transpose. So, this is a rather good advantage for us. It is enough if we remember 1 M and then the inverse is simply 2/3 of M transpose. So, the choice of k has enabled us to get this simplification. This is fine. Next, what do we need to do? We now have this description n alpha beta and ns completed, right? How to determine what is n alpha beta and what is ns? That is the next issue that we have to address. So, let us do that. There are two approaches that can be taken in order to resolve that issue. We are looking at some sort of equivalence between a winding that is placed on the AS axis BS axis and CS axis. That means 3 windings which are there originally, and we want to transform this to 2 windings which is alpha and beta. How do you establish the equivalence? We have said that the first basis of establishing equivalence is that the MMF generated by the two should be the same, only then these two are equivalent. Now other than that, one can also look at the electrical active electrical power consumed by these two, by the entire set. Here on the one hand you have these 3 which are going to consume electrical input power, here you have only these 2 which are going to consume electrical input power. So what one can say is that, say case 1 is when the net power or the total power is unchanged. Which means the net power taken by A phase, B phase and C phase together must now be equal to the net power drawn by alpha and beta which we have. And now of course there is one more variable, 0 phase also. Or one can look at another case where we can say that per phase power is unchanged. So this situation is called power invariancy. This is power invariance, this is non-invariant. So if we take these two, how does the system of equations look like? So let us consider that. You have, let us take the first case, case 1. If the net power which is drawn by the 3 phases must be equal to these two, what we have is I transpose ABC, that means I is a vector consisting of IA, IB, IC, transpose ABC multiplied by VABC, this is a vector consisting of VA, VB, VC. Remember that active power is given by VA into IA plus VB into IB plus VC into IC, which is the same as I transpose ABC multiplied by VABC. What we are saying is this is equal to I alpha beta, now the 0 is also added, transpose multiplied by V alpha beta 0. This is what we are saying. And here we have already derived a relationship between I alpha beta 0 and IABC. What we have is I alpha beta 0 equals ns by n alpha beta multiplied by this matrix M multiplied by the vector IABC. So let us substitute for I alpha beta 0 there. So what you have is IABC transpose VABC equals ns by n alpha beta multiplied by M into IABC transpose V alpha beta 0, and this is nothing but ns by n alpha beta into I A B C transpose m transpose V alpha beta 0. So, what we find is that if the left hand side now has to be equal to the right hand side, we need to define V A B C as ns by n alpha beta into m transpose V alpha beta 0. This is what we get. Now, what we have already for I is that we have I A B C is equal to n alpha beta by ns into m inverse into I alpha beta 0. I have just rewritten the expression that we already have in terms of I A B C. So, it is n alpha beta by ns pre multiplied by m inverse. So, what we see from these two equations is the transformation of the equation which is going to relate V A B C to V alpha beta 0 appears to be a little different from the relation between I A B C and I alpha beta 0. Now, we could retain it like this, but it would be simpler if the relationships between V and I are identical, which means that what we want is ns by n alpha beta must be equal to n alpha beta by ns multiplied by this into m transpose is equal to this multiplied by m inverse. So, this must be equal to this if the two equations are to look identical, that is the manner in which alpha beta has to be transformed to ABC is the same for V and I, then this part should be equal to this part. But we already know from our earlier expressions that we have derived, m inverse is nothing but 2 by 3 times m transpose. So, this can be written as n alpha beta by ns into 2 by 3 times m transpose, and therefore, what we get is that if this has to be true, then ns square by n alpha beta square should be equal to 2 by 3 or ns by n alpha beta should be equal to root of 2 by 3. So, if you choose ns by n alpha beta, that is the number of turns on the alpha beta winding here, and of course, the number of turns in the alpha winding is the same as the number of turns on this winding, these two are identical. Similarly, the turns on A, B, C are identical. The ratio of those two turns is what we have derived. If it is equal to square root of 2 by 3, then what we are saying is that the net input power is invariant. It is the same in the ABC system as well as in the alpha beta system. So, this is one approach. Another approach is as we have seen the second case, that is what we are saying is case 2 is I ABC transpose multiplied by V ABC. This is a 3 phase system and per phase active power is this divided by 3. If we look at the alpha beta system, I alpha beta 0 transpose into V alpha beta 0 by 2. Now, why are we saying this is 2 in spite of having written alpha beta and 0? The reason is we know that if we have a a system of AC voltages which are balanced, then the zero sequence part will go to 0, and by and large we deal with electrical systems which are of this nature, and in most cases therefore zero sequence will go to 0, and therefore the active electrical input power is then consumed only by the alpha and beta and not by this part which is this, and therefore we consider this to be having only two phases. So if we have this and then we substitute the expression for I alpha beta 0 again as before, what we have is I alpha beta 0 is ns by n alpha beta. So ns by n alpha beta multiplied by m into I ABC transpose multiplied by V alpha beta 0 into 1 by 2, which is the same as ns by n alpha beta multiplied by I ABC transpose m transpose V alpha beta 0 multiplied by half, and this has to be equal to I ABC transpose V ABC by 3. And looking at this equation, we can therefore conclude that these two expressions will be identical if VABC is equal to 3 by 2 times ns by n alpha beta multiplied by m transpose into V alpha beta 0. And we already have a relationship for IABC. IABC is n alpha beta by ns into m inverse into I alpha beta 0. So again, looking at the same argument that we would like the relationship to transform V alpha beta 0 to ABC to be the same as the relationship that transforms I alpha beta 0 to IABC, we would need to have this part of the expression and this part of the expression to be the same, and therefore we can derive another condition. So what we want is 3 by 2 times ns by n alpha beta multiplied by m transpose should be equal to n alpha beta by ns into m inverse, and we know that m inverse is 2/3 of m transpose. So 2 by 3 times m transpose. Therefore what you have is these two terms will be equal if ns square by n alpha beta square is equal to 4 by 9, which means that ns by n alpha beta is equal to 2 by 3. So on the one hand, if you want to have invariance of the electrical input power, you need to choose ns by n alpha beta to be root 2 by 3. If you want to have input power per phase to be equal, then you need to choose ns by n alpha beta to be just 2 by 3. And what is the implication of these two? So with this then we can now try to find out what is the relationship between V and I. So let us look at VABC. VABC in the second case is 3 by 2 times ns by n alpha beta is 2 by 3 times m transpose into V alpha beta 0, which is nothing but m transpose into V alpha beta 0. Similarly, obviously IABC will also be equal to m transpose into I alpha beta 0, because we have intentionally said that the equations transforming V and I should be the same. One can now look at the inverse also, then V alpha beta 0 is equal to M transpose inverse into V ABC, which is then M transpose inverse is M inverse transpose into V ABC, and M inverse is nothing but 2 by 3 M transpose into V ABC. So, this is 2 by 3 times M into V ABC. So, you get this extra factor 2 by 3 as compared to what you had here. Similarly, you will have an expression for I alpha beta 0 also. So, in the next lecture we will see how the equations relating V ABC and V alpha beta 0 for the invariant case are going to simplify with the choice of ns and n alpha beta 0. We will stop here for this lecture.